The DualSense wireless controller for the PlayStation 5 has several cool features. Perhaps most interesting is its immersive haptic feedback and adaptive triggers. Previous PS controllers use rumble motors to give haptic feedback. This controller uses more sophisticated haptics to simulate the feeling of weapon recoils and numerous other game actions. Also included are adaptive triggers designed to let gamers experience varying levels of force and tension geared to what's going on in the game. Typical examples being pulling back on an increasingly tight bowstring or hitting the brakes on a speeding car. There is also a built-in microphone for chatting with other gamers and a special button for broadcasting adventures to buddies.
The disassembly begins by prying off a plastic trim cover which hides 4 Phillips screws. Removing this allows the removal of the top of the case. This lets you see the 5.7 watt-hour lithium-ion battery, the haptics motors, and the adaptive triggers. The battery attaches to the PCB via leads and a connector so it can be removed. Behind the battery sits the rear-facing microphone and the plastic well holding the battery attached via another Phillips screw. Removing the plastic well reveals the motherboard. The motherboard, joystick, and haptics vibration motors all sit in the plastic frame.
The joysticks are soldered to the motherboard. Reports are that these joysticks are the same type on earlier PS controllers, and much has been written about their shortcomings. The principal problem is that these joysticks can drift and wear out after not all that much use. The main wear-out mechanism seems to be the 2 potentiometers that sense X and Y direction. The potentiometers contain a metal wiper that slides on a resistive surface, so over time the resistive material can wear off and form debris that fouls the joystick sensing. The joystick also contains a spring that returns the joystick to a centered neutral position when the user lets go. It has been widely reported that the spring can stretch ever so slightly, creating a new neutral point. The wear problems of the joysticks become clear when you consider the findings of iFixit, a site that teaches people how to fix things. iFixit looked at an Alps joystick similar to that used in the DualSense controller and learned that its potentiometers had an operating life of 2 million cycles. The center push function was only meant to last 500,000 cycles. iFixit figured that based on some typical Call of Duty gameplay, the components in these joysticks could easily reach the end of their operating life in just over 400 hours of game time.
As an aside, it would seem Hall effect non-contact position centers might provide a longer life than wiper-based potentiometers. With all the engineering that went into the PS5 console, at least to us, it's unclear why the designers chose the direction they did with regard to the joysticks. Moving on to the motherboard, you find 4 main ICs. One is likely a custom processor by Sony. A PMIC chip from Dialog manages charging, discharging, and power use, and is specifically designed for wearables and home automation uses. A chip from Realtek seems to be a custom version of an audio codec chip. The other chip is also from Realtek and seems to be an audio amp. Though the PS5 controller does have a speaker, the purpose of the 2 Realtek audio chips may not have anything to do with generating sound. They may be there to power the haptics motors. Previous generations of PS controllers implemented haptics via old-style vibration motors, which generated movement from eccentric masses on the motor shaft. In contrast, the PS5 controller uses linear resonance actuators, or LRAs, made by Foster in Japan.
LRAs use a movable mass, permanent magnets, a voice coil, and wave springs to generate vibrations. The voice coil produces a magnetic field which interacts with the permanent magnet, moving it in a way that compresses or stretches wave springs on either end of the vibration motor assembly. So in a way, LRAs act like the cone of a loudspeaker. The drive signal must be AC, hence the need for the audio amplifier codec. The AC drive signal oscillates the magnetic field to make the permanent magnet move back and forth against the two wave springs, generating vibrations. LRAs tend to be more sophisticated haptic vibrators than eccentric mass motors. They typically exhibit shorter lag and rise times than eccentric motors, which is important for simulating short duration effects. They also tend to consume less power, and it is possible to vary the amplitude and frequency of their AC drive signals to get richer haptics than with ordinary eccentric mass motors.
There are some electronics behind the black frame worth looking at. The black frame comes off by removing two screws from the frame arms. This lets you pull the frame, motherboard, and vibration motors out of the other half of the outer case. Also attached to the black plastic frame behind the motherboard are a white touchpad bracket and a clear light guide that lets an LED on the motherboard provide lighting. Behind the black plastic frame is the touchpad. There's a PCB glued to the pad surface that doubles as the touchpad sensor. The PCB, nestled behind the touchpad plate, also contains the IC managing the touch functions, a microchip touchscreen console IC. There's also a simple on-off push-button switch on the touchpad PCB, and also residing on this part of the outer case are the 8 button pads.
2 Phillips screws hold each of the trigger modules to the frame. 4 other screws hold the trigger module case together. Removing them gives a view of the switches themselves and the mechanism used to vary the tension on the trigger lever. The trigger modules feature a trigger resistance that can be varied by the game software. This dynamic push resistance comes via a motor and worm gear that drives a gear-actuated plastic stop, which pushes against the push switch. The farther the worm gear moves the stop, the more resistance gets applied to the push action of the switch. Basically, the added resistance comes from pushing against the motor torque as applied through the worm gear, ring gear combination. This gear set portion is recorded via a potentiometer on the module PCB. An unlabeled ICB on the module PCB seems to be handling the switch functions. Interestingly, the right-hand module differs from the left-hand module. Inside the right-hand module is what seems to be a 2-position sensor able to detect both partial and full trigger pulls. In contrast, the left-hand module contains a simple on-off switch.
And those are the high points of the PS5 DualSense controller. For more video teardowns like this one, go to eeworldonline.com.